Okay, here we go for the last topic of today, which is the numerability. Numerability is quite delicate. I don't want to face all the theory of numerability because it is quite technical, quite complicated. It's far beyond our scope. But just to give you some hint about that. So the first thing is, remember when I talked about bijections, I said that two sets, this is the principle, two sets can be put in one-to-one correspondence if and only if they have the same number of elements. Think of the fingers of the hands. There are 5 for both hands, so you can make them correspond one to another. Okay, this is the easiest example if you want. And I told you this is quite obvious when we deal with finite sets, so sets with a finite number of elements. This is much less obvious when you are dealing with infinite sets, so sets with an infinite number of elements, like the sets of numbers. So not obvious when the considered sets have infinitely many elements. So to say, they are infinite sets. So the key point here is whether when you consider an infinite set A, is it possible to make a list of the elements? List means that all elements appears. It appears only once, but this is less important. The important fact is that all elements appear. A list that includes all elements. So example, the first example is very easy. The list of naturals. List of naturals is very easy. 0, 1, 2, 3, and so on and so on. Essentially, making a list means create a one-to-one correspondence with the naturals. Because, for instance, you can also organize a list of integers. So 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. You can list them, and again, listing them means exhibit a one-to-one correspondence with the natural. For instance, here 0 corresponds to the 0. It is at the first place in our list. Then 1 with 1, minus 1 with 2, 2 with 3, and so on and so on. So, making a list, it is nothing but an informal way to say establish a one-to-one correspondence with the naturals. And since we said at the beginning that the basic concept of this theory of counting elements is that two sets can be put in a one-to-one correspondence if and only if they have the same number of elements, the conclusion is natural and integers are of the same size, so to say. The exact word is that they have the same power. We say of power of an infinity. So, namely, the infinite of naturals is as large as the infinite of integers. Even though this is highly counterintuitive, because integers are, in some sense, more than the natural because they include it. So notice that apparently this seems to be in contradiction with the fact that n is a subset of Z. How is it possible that they have the same size when one is strictly contained in the other? This is a basic feature of infinite set. Indeed, in the set theory, a set is infinite if and only if it can be made in one-to-one correspondence with a proper subset of its. In the true axiomatic set theory, this is the definition of infinite sets. So try to reason of that. The first time you have to cope with this fact that integers and natural have the same number of elements, but also, so as an exercise you can prove that also even numbers and odd numbers and so on have the same power, which is the correct word, the mathematical word for the same number of elements, of the same power of n. Like definition, sets that can be put in one-to-one correspondence with n, so sets with the same power of n are said countable. And now the first probably shocking result, theorem, is that not only the integers, not only the even and the odd are countable, but also rationals are countable. Rationals seem to be much more than integers and than natural, but it is not true. They have the same power. Why? Because it is possible to do a list with rationals. We already did some videos ago. We can do it again. And what is surprising about this fact? What is surprising is that the list of naturals doesn't follow the growth of naturals. So you cannot say 1, 2, 3, like for instance for naturals. For rationals, you have to do another list. And again, here we have the p, here we have the q's, and so here we have 0, 1, 2, 3, 4, 5, and here you have 1, minus 1, 2, minus 2, and so on and so on, 3, minus 3. So in the first, here are a couple of p and q, so in the first column you always have these zeros. Here you have 1, minus 1, 1 half, minus 1 half, 1/3, minus 1/3, and so on. Here 2, minus 2, and again 1, minus 1, 2/3, minus 2/3, and so on. When doing this table, you capture all naturals. Indeed, you capture more than all naturals. You see the 1 is already repeated several times here. 1 is here and here, but this is not important. Now what you want to do is simply to count all elements of this table. And you can do it quite easily. You start here from 0, for instance, then you go to 1, then you go to 2, then you go back to minus 1, then you go back to minus 2, then you go back here and here. So you have to do a path here that covers all dots, and you can do that. This is a way of counting the rationals, but you can do also like we did in a previous video with the other table. Where is the table? Here, probably it is less spectacular, you don't have to find paths, but here it is clearer how to construct a list of rationals. So, the point is that here it is possible to draw a path that meets all points in the table. This gives automatically a list of rationals. Moreover, these rationals are repeated infinitely many times. Therefore, Q is countable. Now you can suspect that all infinite sets are countable, because also Q, which seems to be so large, is countable. And R is just Q, but with some gap filled. But here the result is the second stunning result of today, a very beautiful result that says R is not countable. Okay, this is extremely deep result, which is due to Cantor, and it has a genial proof. And the proof is the following. Again, it is very difficult the first time, so read it again and again and again. The proof says, by contradiction, suppose R is countable. Therefore, you are given a list of all real numbers. And this list is made like that. There is the first number, which is n1 dot, and here you have beta of the first number, first digit, beta of the first number, second digit, beta 1, 3, up to beta 1k, and so on and so on. This is the first, let me call it x1. The second real of the list is n2 dot, first digit of the second number, b22, b23, up to b2k, and so on and so on. And then you go to the nth number, which is n dot bn1, bn2, and so on and so on, bnk. Okay? Now, I want to show, we show that there is a real number not included in the list. A real number not included in the list. How is it made? So, first, consider just the digit part. You call it gamma. You say 0 dot, gamma 1, gamma 2, up to gamma k. And you choose gamma 1 in this way. Gamma 1 is equal to 5 if b11 is different from 5. 7 if beta 11 is equal to 5. So what happens here is that gamma 1 is different from beta 11 because of this prescription. And since gamma and x1 differs for the first digit, of course they have to be different numbers. So you have that gamma different from x1. Now you go to gamma 2 and you do exactly the same but with beta 22. 5 if beta 22 is not 5. 7 if beta 22 is 5. Again, gamma 2 is different from beta 22 due to this prescription, and then gamma is different from x2. So what happens here? Here it happens that we already constructed a gamma which is different from the first two numbers of the list, and notice that it is different from the first number only because it is different, its first digit is different from the second number only because the second digit is different, and so on and so on. We follow the list along the diagonal and we construct a number which differs from every number due to possibly to the only element on the diagonal. So in general, we have gamma k is equal to 5 if beta kk is different from 5, 7 if beta kk is equal to 5. So gamma will be different from xk for every k. So gamma is not in the list. But it is a real number because its structure. There is a digit part and an integer part. Moreover, it is a real number with only one expansion, with only one representation, because there are no 9 nor 0. So with unambiguous. End of the proof. Think of it. So as an exercise, I can suggest you to prove that square root of 3 is irrational, and if n natural is that square root of n is rational, then n is a square for some k in n. Okay, this is the end. Thank you very much. See you on Tuesday for the question time on this lecture. Bye.